In this video, we're going to compare gravitational fields with electric fields. So before we begin with anything else, I want to talk about how the biggest difference between the gravitational fields and electric fields is that at this level, gravity is only attractive. So electric fields can attract or repel because we know that there are positive charges and there are negative charges. Hence, there are positive and negative fields, right, for electric fields. However, for gravity, we've only talked about attractive fields. The Earth is attracted to the sun, the moon is attracted to the Earth, but we have not yet heard of a case of mass repelling another mass. And actually, as things get more complex, there is a thing called negative mass, which can also give a negative field. But it's important to remember that at this level, which is, year 12 physics, gravity is only attractive. That's the biggest kind of opposing difference. We can start talking about the origin of the fields, right? The origin of the fields for gravitational fields are from masses. Masses are the ones that create the forces that attract other masses together. For electric fields, it's obviously electric charges. Opposite charges will attract and same charges will repel. And then we talk about which type of forces there are. So for vector forces, right? For gravitational potential or gravitational forces, there are only gravitational attractions. There are no repulsions. For electrical forces, then we have both electrical repulsion and attraction, and they're both possible. Let's talk a little bit about gravitational fields. For every single gravitational field, the gravitational field strength G, that is, on Earth it's 9.81 meters per second square, is denoted by this equation. G is force per mass. So basically, it's how much force is exerted per unit mass, and this mass is going to be in kg. This is going to be in newtons, and so basically, G is newtons per kg, as we see here. G is in newtons per kg. And this can also just equal to this. If you we know that force is ma, so Newton is kg times m times s to the power of -2. And then we multiply this part of it times kg to the power of -1. These two cancel out, and that's what we get. So we know that happens, and the field strength is force per mass. For electrical fields, the field strength is denoted by E. It's a capital E, and that gives us the field strength. That is the force over charge, force over Coulomb. And the field strength is force per unit positive charge. And this is, obviously, Newton per Coulomb, or volt per meter. And you might know that it is an alternative equation for getting the field strength of an electric field. If you have a uniform field, it just goes like that, you can just take the difference in voltage and divide it by the difference or the distance that separates these two things, and then you're going to get that. And obviously we can see that the units will be voltage out of meter, voltage per meter. So that is basically how we get the field strength for both types of fields. So going back to our topic of uniform fields, for gravitational fields, they have a parallel gravitational field line, and it is also that G is a constant. For electrical fields, we have parallel electrical field lines. We have an additional equation for this, which is V over D, and that is also constant. And, might I remind that this is 9.81 newtons per kilogram, or it's also meters per second square. So, yeah. And then we have spherical fields, or radial fields is another word for that. For gravitational fields, the radial field lines, there are the forces given by Newton's law. So you can imagine, let's say we have Earth, right? This is Earth, and it would have field lines going like this. So this is our radial field lines for a certain circular, or in the case of Earth, nearly circular or spherical mass, a body mass. So we have separate equations for radial fields, right? We have an equation for uniform fields. We have a different equation for spherical or radial fields. And the equation for gravity and gravitational fields is force is G, which is the unit, it's a constant, right? Times M, capital M points to the body that is producing the force, small letter m, which is maybe like the little body that the force is acting on, divided by r squared, which is the distance between these two. That's r squared. Field strength is therefore G is gm divided by r squared, because field strength we know is the force per mass. So if we divide that by mass, these two will cancel out, which gives us that. Now, the gravitational field lines are always attractive, and this is why we see this sort of graph. So you might have heard in the last video that I did on electrical potential that if you have an attractive field, then the fields are always going to be negative. So negative means attractive field, positive means repulsive field, and therefore they are always negative. There is always a negative field for gravity, at least up to this point. And so they obey an inverse square law with distance. And you see here on this graph that the inverse square law is followed, but it's not followed going down like this. It's going up like this, right? And this is because of the fact that it's always going to be negative. The further the distance becomes, the smaller and closer to zero G will become. And then at infinity, R equals infinity, maybe this would touch, and then it would become a zero at infinity, theoretically. Now let's talk about electrical fields that are also produced by spherical objects. So they also have radial field lines, and the force is given by something called Coulomb's law. So note the difference. Over here, we're using Coulomb's law. Over here, we're using Newton's law. Two different people, and they have a very similar sort of they have a very similar form of equation. We have Q1, which is the charge that is producing the field, Q2, which is the charge that is being affected by the field, and then this is a constant times r squared. So basically we know that 1 out of 4 pi epsilon, this is a constant, so it's actually kind of just Q1, Q2 divided by r squared times constant. So assuming that this is a constant, right? Don't let this going underneath fool you. Actually, the form of the equation is very much similar with the previous one that we looked at. Right here, where we also times both of them together, divided by the separation, and we basically multiply a constant to it. So a negative charge gives an attractive field, and a positive charge gives a repulsive field for electrical fields. And there's only negative for gravitational fields. And we also have to think about field strength. We divide that by the second charge, Q2, so we get this. Force and field strength obey an inverse square law with distance. And we can see that right here. So if you have a positive charge, it's going to give you a positive electric field strength. If you have a negative charge, it's going to give you a negative electrical field strength. This is going to lead to a repulsive field. This is going to lead to an attractive field. Now let's talk about potential. So gravitational potential. So this is denoted by Greek letter phi. And we have gravitational potential is negative the constant times the mass that is producing the field divided by the separation. So the potential obeys an inverse relationship with distance and is zero at infinity. And so as for potential, we're talking about the sort of energy per mass of a certain object, right, in this field. And so it is a scalar quantity because this is energy. And you can also see that the mass of the smaller object that is being affected by this bigger object, it is not included in the equation, telling us that it doesn't matter what your mass is, it just matters how close you are to the thing that's producing that field. And it is always negative, as we can see. So it is always negative, and it becomes zero at infinity. And we can picture potential wells again. We are in a potential well. This is Earth, Sun is also in a potential well, and if you go to infinity, then the gravitational potential would become 0. So this is Earth, this is, and we see that there are only potential wells for gravitational potential at this point, which is not the case for electrical potential. For electrical potential, we have V, that is the representation, it's measured by volts, is defined as the charge that is making or creating the field divided by the constant 4 pi epsilon, and also divided by the separation. And this is also obtained by integration of the Coulomb's law equation. So it also obeys an inverse relationship with distance, and it is 0 at infinity, and it is a scalar quantity. And electrical potential also has a very similar graph. This is a positive charge, negative potential, positive potential. And so that is about it for this video on a simple comparison of the things that we've learned about when we talk about gravitational potential, gravitational fields, and electrical fields. I also have a lot more videos posted on similar topics, as well as just physics at the year 12/A level in general. And so if you would like to watch more videos on those, then it would be amazing if you would check my channel out for more videos. So if you enjoyed, then please do subscribe, and thank you for watching.